Cavalcanti from Utrecht University, who's going to tell us about stable generalized complex geometry.
Thanks for the invitation. It's nice to be here again. It's very nice to see Australia and Brazil together. And I believe half of you guys are very asleep, and the other half probably also very asleep because it's the time for the siesta or something. So I can be very kind and do this. Maybe not. Anyway, it's nice to see you guys here, and it's nice to be back in Rio. So I'll talk about stable, generalized complex structures. This is joint work mostly with Marco Gualtieri, but part of it is also with my PhD student, Ralph Klasse. So let me just start telling you guys a little bit about generalized complex structures, because I think that I'm assuming that not everybody knows about them. Maybe you have heard of them at some point. So let's just have a quick introduction on generalized complex geometry. First, there is one definition, but in fact there are three equivalent ones, and every now and then we use a different one. So it's good to keep in mind that there are three different definitions. The first one is the one that kind of gives it its name. So it should be something that looks complex. And in fact, so the first thing to keep in mind is the space where you should define this. So it should be some structure in some space. And normally you have a structure on a manifold, but from our point of view, it's better to think as the space as being a manifold with a tree form. So that's where you put your structure, okay? So first you have to give you a manifold with a closed tree form, and then I can start talking about putting generalized complex structures on it. So what is a generalized complex structure? It should be just a complex structure on the sum of tangent plus cotangent bundle. In T plus T star have the natural pairing of vectors on forms, and it should be orthogonal with respect to this pairing. So this is the symmetric pairing that picks a form evaluate on the vector. And should be integrable with respect to the Courant bracket. I'll get back to that in a second. But that's kind of the one that makes it look like a complex structure, a Hermitian structure on a manifold. A completely equivalent definition comes by looking at the plus eigenspace of this endomorphism. So what is that plus eigenspace? Because it was compatible with the pairing, it turns automatically to be a complex Lagrangian subbundle of the complexification of T plus T star. And because so L is the plus eigenspace. And if you look at how the plus eigenspace intersects the minus eigenspace, they should not intersect. So that's a property you should get. And integrability, that I didn't really specify before, it should be that L is involutive with respect to Courant bracket that we heard about last talk. So there's a completely equivalent way to describe generalized complex structure. You could quite well look at these subbundles of T plus T stars that find this collection of conditions here. And a separate way to describe generalized complex structures, it's also very useful because it brings forms into the picture, is to look at this a form which annihilates this space. So T plus T star x on forms by T x by contraction and T star x by wedge. So you can look at the space of forms, a form that annihilates this space. So here you have a much longer definition. So generalized complex structure is a complex line bundle which sits inside the complex forms. And it should be pointwise of a very specific form, namely this one here, should be the exponential of a complex value 2 form, wedge a decomposable K form here. And once it has this algebraic type, you automatically get the space of elements in T plus T star which annihilate this form. So once you contract and wedge, it's maximum isotropic. And then you have this non-degeneracy condition that comes in, which is that if you wedge these guys together to get a top degree form, you get something which is non-zero. And that has to do, is precisely equivalent to saying that L intersect L bar is trivial. And finally, there is the integrability. I never told you what the Courant bracket is, but if you have a non-vanishing section of this bundle here, it should satisfy something like this. So if you take the derivative twisted by h, it should be the same thing as the action of an element in T plus T star on that same guy there, same section, okay? And essentially, I have no use for the Courant bracket, but essentially the Courant bracket is something that you cook up out of the exterior derivative twisted by h in the same way that you cook up the Lie bracket out of just the exterior derivative. So it's a natural extension of the Lie brackets to T plus T star. So these are the three definitions of generalized complex structures. Why were they interesting? So they're interesting at first because of the examples. The first example, the simplest one, is if you have a complex structure. So I can actually go and check, that's an exercise if you like, that you can define it using any of the three definitions. But in this case, I'll just pick the last one. I should give you a complex line bundle satisfying the property, the properties I just mentioned. So you just take this line bundle K to be the canonical bundle of your complex structure. So that's generated by dz1, wedge dz2, etc. So it's automatically generated by a decomposable complex form. And if you pick one such form and wedge if it's complex conjugate, it's non-zero. It's a volume form. So right away you see that complex structure gives rise to a generalized complex structure. Locally it's dz1, dzn, so locally d of that is actually 0. So it satisfies all the properties that you need. So that's the first example. It's not surprising, otherwise you'd not call it generalized complex, right? It should at least have complex structures. The other example that was more interesting, more surprising from the definition, but it came out right away as well, is that a symplectic structure is also an example of generalized complex structure. Namely, just take this K, the line bundle generated by e to the I omega, where this is the symplectic form, and you can go back to your definition and check that it actually satisfies all the correct algebraic properties, integrability, and so on. So these were two examples that came out right away, and right away people thought these generalized complex structures were interesting because they unified complex and symplectic geometry under one roof. So that was one good thing. There were more examples. For example, you can look at a holomorphic Poisson structure, and what you can do, so that assumes that you have a complex manifold, and on top of having a complex manifold, you still have this bivector, which is at the same time holomorphic, and Poisson. So these are two independent conditions. So if you have such a thing, you can use this bivector to deform your structure. So pick the line that I had before for the complex structure, and you contract this line with the exponential of pi, okay? And out of that, you produce something new. So the holomorphic Poisson conditions are precisely what you need for this thing to be integrable. And that gives you a new example, and that was an interesting one, because if you were to look at what this structure looks like, well, actually, we don't know very much about that. But for example, if this Poisson bivector was non-degenerate, so if its top power is non-zero, then it actually transforms the complex structure into a symplectic one. So holomorphic Poisson, the holomorphic symplectic structures, right away, can be connected to complex structures. So not only complex and symplectic are examples, but in some cases, you can deform one into the other. So these were things that were interested in. They were noticed by Hitching right away in his first paper on the subject. You can look at a little bit slightly different. It still fits in the setup, but not as nicely behaved as the holomorphic symplectic. But it's still a holomorphic Poisson structure. So pick a holomorphic Poisson bivector, namely this one here. So I mean C2, every bivector is automatically Poisson. So like once it's holomorphic, and it's holomorphic because you just have this holomorphic function. Here's the coefficient. And you can just perform this contraction here. So you have so you really do e to the z ddz ddw applied to the canonical bundle of your complex structure, which is dz dw, if I got it right, maybe dw dz. And this is going to be equal to, so just expand the exponential. One times dz dw is just dz dw. But that's the higher degree part, so I'll put it at the end. And this bit here contracted with dz dw, well, depends on your convention. I'll just call it 1 for now. So this gives me 1, and I just get z. So this is a generalized complex structure as well. And it's useful to write it in two different ways. One of them is that it is z times e to the d log z dw, if z is non-zero. And it is just dz dw if z is 0. Okay? So when you look at it like that, you see that in this one generalized complex structure, this is somewhat reminiscent of the symplectic structure. In fact, it is a symplectic structure. And this is just what we described as a complex structure. So it's one generalized complex structure in a manifold, which has at the same time complex and symplectic points. So not only can you deform one into the other, but even in a single manifold, complex and symplectic points can coexist. Okay? So general aim, so like let's say you think generalized complex structures are an interesting thing, then just from the point of view saying, okay, if these objects are interesting, I should learn something about them. And that's what I'd like to try to do today. And there are some basic questions you should ask, like you'd like to have answered at least. One of them is, what do they look like? If these guys are interesting, what do they look like? Can I have Darboux coordinates or something like? Or if I have a submanifold, do I have nice coordinates around submanifolds? If you think of complex and symplectic geometry, we always have Darboux coordinates on both. But when you look at submanifolds, normally in the symplectic world you're fine, and in the complex world you're not. And also, there is the question of, are there relevant subtypes? So we kind of have already established that there are at least 3 important subtypes: complex, symplectic, and holomorphic Poisson. Okay? And you might wonder if there are other types that seem to be worth studying. That we look at them and seem like this is a natural subtype of generalized complex structures that deserves attention. Okay? So these are the 2 things that I'd like to kind of do today. I'll tell you a little bit of what things look like in general. I'll propose some relevant subtypes and try to tell local forms about these subtypes and see something about the techniques we use. So this is the structure of the talk. I'd like to tell you a little bit about generalized complex geometry in general still, a bit more, just to kind of elaborate a bit more on the definitions. Then I'll introduce the subtype that I'm interested in today, so stable structures. And stable structures will be defined from generalized complex structures in terms of this line bundle that I already introduced, and a section of that line bundle. And at that stage, we kind of take a step back and say, well, actually, there seems to be, surprisingly, rich geometry behind a complex line bundle with a section. So here, I'll take a big step back, and I'll just start studying complex line bundles with sections. And I think I'll take a further step back and do something similar for real line bundles with sections as well. And after studying all of that, hopefully, I'll be able to tell you something a little bit better about these stable structures. So they'll shed new light that will make stable structures more tangible. And eventually, they'll become symplectic structures somewhere else. And once they became symplectic structures, I can use symplectic techniques to study them. And I get results from symplectic geometry that can be translated to these things. So that's the end of it. Hopefully, I'll be able to tell you some, at least, of the symplectic techniques you can use, okay? So this is the structure of the talk, and let's start with generalized complex structures. Are we okay? Okay. So again, the definition number 2 was that a generalized complex structure was a complex Lagrangian subbundle in T plus T star complexified, for which this property held, and it was involutive. So if you remove this property here, that's a bit too much, you get what we just call like a Dirac structure. It's a Lie algebroid. So it's a complex Dirac structure. And whenever you have a Lie algebroid, you get a corresponding de Rham theory. So you have a bracket, you have an anchor. So using these 2 things, you can define an exterior algebra, an exterior derivative on the exterior algebra of the dual. In our case, because of this condition, we can also identify the dual space with the complex conjugate, because the pairing is non-degenerate. So I get automatically that this guy here has a differential on it and a corresponding cohomology theory. Okay? So that's the first thing. There is some extra stuff that comes out of this definition number 2 that comes from the theory of Lie algebroids. Now, the definition number 3 was long and whatnot. And one thing that came was that if you have the integrability condition here, I asked for something which was in T plus T star real, for which this equation held. But I also described that the rho should be whatever annihilates L. Okay? So if you pick anything in the plus I eigenspace, it should be killed by rho. So if you decompose this V into plus I and minus I components, the plus I component will kill it anyway. So instead of putting T plus T star, I might quite well have put L bar there. And now it's something that belongs in this Lie algebroid complex and is automatically closed. So this guy here becomes like, whenever you have a local trivialization, you have right away a closed form. And you can start looking, if you change your trivialization, this closed form changes by something exact, and therefore you get a cohomology class associated to your generalized complex structure, as long as you can find global trivializations, or in whatever your global trivialization is defined. So just some names. This line bundle that I have been talking about following the complex structure case is called the canonical bundle, because in the complex world it was the canonical bundle, so you might quite well keep that name. The type of the structure is the degree of this form omega. So in the complex case, the type is maximal, is n. In the symplectic case, it's the exponential of I omega, so it starts with 1 plus, etc. So there the type is 0. So these are the 2 extremes. Symplectic is the generic one, and complex is the most particular one, which has type n. And this example here already tells you that the type can jump from point to point. It's one of these semi-continuous of one type or another function. So it's generically 0, and then it becomes 2 at some points. So it doesn't have to be constant. This V that I was introducing before is the modular vector field, and the cohomology class it defines is the modular class. And we say that a generalized complex structure is generalized Calabi-Yau. if this canonical bundle has a nowhere vanishing closed section. Okay, so that was the one that Hitching originally studied. Like the first paper on this was on generalized Calabi-Yau things, although back then there was no age. So symplectic structures are automatically generalized Calabi-Yau. They have a globally defined section. In the complex case, you need the canonical bundle to be holomorphically trivial. So that's what a generalized Calabi-Yau would look like in the complex case. Another thing, just so, like, how can I think about them if I have not seen these generalized complex structures before? I have no idea if people here in the audience have not seen them before, but if you have not, one way to see that, to think about them is a good first approximation, is that you can pick T star and apply J to T star. So that gives you some subbundle of T plus T star. And you project the subbundle down to T. That gives you a distribution on the tangent space. And because of the whole generalized complex conditions, you get that this distribution is in fact singular, and it's a singular integrable distribution. So the rank can jump, but it satisfies the correct hypothesis, so you can actually integrate this. And the leaves of the distribution are always symplectic. So that's a Poisson structure. So right away, out of a generalized complex structure, you get a Poisson structure. And further, if you look at the transverse space, it always has a transverse complex structure. So it's not quite a product, but nearly. So that's like a first approximation to generalized complex. You could think of it as symplectic foliation with transverse complex structure, if you have not seen these things before. Okay, so if you like to translate to something more classical. So that's a few things from generalized complex geometry. Canonical bundle, the type, this modular class. If the modular class vanishes, you get generalized Calabi-Yau, and an intuitive way to think about it if you have not seen them before. Okay. So what is the local structure? What do these structures look like? I guess that's like a basic question that you'd like to see answered quickly, I guess. So the first answer came right away in Marco's thesis, Gualtieri's thesis, which was if the type is not jumping. So if the type is constant in a neighborhood of a point, you can right away just play around with the differential geometry and check that your generalized complex structure is actually a product of complex and symplectic. So that's first idea that should be symplectic times complex actually holds on the nose. Generalized complex is symplectic times complex. But if the type changes, that's something that's a little harder to treat, but eventually, Bailey, who was Marco's student, came with an answer as well. So in a neighborhood of a point, we have a good understanding somewhat of a generalized complex structure look like. Namely, it's always going to be the product of something symplectic and a holomorphic Poisson structure which vanishes at the point in question. Okay, so it's like Weinstein splitting theorem for Poisson manifolds. You have something similar here. You can split out a symplectic directions, and you're left with something which is complex at that point. And once something's complex at a point, in a neighborhood of that point, it must be holomorphic Poisson. Okay? Doesn't fully answer, but like it already answers a lot, the question of what do they look like. It essentially translates the question about generalized complex structures to the question of what do holomorphic Poisson structures look like. I don't know what they look like, but they are holomorphic, and that in itself is much better already. Okay? So being holomorphic itself is already a strong condition, and on top of being holomorphic, you have a further differential condition that you have to put on this bivector. So, okay, it allows us to use all sorts of complex geometric techniques to study these things. So in principle, this is a good thing to have. Even though we do not know what holomorphic Poisson structures look like, I think a common question there is if you give me one, you can linearize it, is it equivalent to its linearization? Normally it's not, and we don't know what they look like. But at least simplify the question quite a bit from the general one we had before, okay? So next thing I'd like to say is to introduce stable structures. And to introduce those, I'll just get back to the canonical bundle. And in fact, I'll go to the dual of the canonical bundle, the anti-canonical bundle, and that one always has a section. Namely, if you have a spinor row, a form row, which is a section of your canonical bundle, the section applied to this anti-canonical section applied to your canonical section should give me a function, and the function is the degree 0 part of this row, okay? So rho is a multi-degree form, and S applied to rho just gives me the degree 0 part of it. So that is right away an anti-canonical section, and it's 0 if rho, at the points where rho has no degree 0 component. So the points where S vanishes are the points where the structure is not symplectic. So this S is good to identify symplectic or non-symplectic points, okay? Vanishing of S is the points where the structure is not of symplectic type. So if you look at this example here, You see that if z is not 0, then S of this guy would just be z, and I would get that it's not 0 and it's of symplectic type. And on those points here where the structure is complex, I actually would get that S applied to this guy is 0 because there is no degree 0 component. And I see that it's not of symplectic type. In fact, it's complex type. So that's the definition of a stable structure. A stable structure is one for which this section S has only non-degenerate zeros. So it seems to be like a rather stable condition. If it had no zeros whatsoever, I would be talking about symplectic manifolds. So I'm trying to single out a class of generalized complex manifolds which are close to being symplectic. They are close, and the way they fail to be symplectic is very well behaved. It's not only that S is generally speaking not 0, but in fact it has like it cuts out 0 transversely. So you have good control over the way it fails to be symplectic. Now I can go back and use Bailey's result and say, well, if this thing here has non-degenerate zeros, then the structure should be locally a product of something complex and something holomorphic Poisson and something symplectic. Play a little bit with it, and then right away I arrive to the thing that it should be r to the 2n minus 4 with symplectic structure times C2 with this structure I have just mentioned here in the example. So this locally is what the stable structures look like. No other way for them to, they don't look like anything else. It's always the same thing. So here we do have some invariant, which is, are you in the singular locus of the Poisson structure or not? If you're not in the singular locus, you have Darboux charts. If you're in the singular locus, you look like this, okay? So no further invariance, just are you in or not? Okay. And then, okay, so out of this discussion here, I've singled out a type of generalized complex structure which comes from a line bundle, complex line bundle with a transverse section. And at that stage, we realized that we didn't know enough about line bundles with transverse sections, so we started studying those first. So let's step back here and look at just line bundles with transverse sections. That's what we call a complex divisor. So a complex divisor for us is going to be a complex line bundle with a transverse section. If you give me a complex divisor, I can right away form an ideal in the smooth functions, a complex valued smooth function on the manifold. Namely, I pick all the sections of the dual bundle and evaluate on the given section. That gives me an ideal of C-infinity functions. And I can look at the vector fields which preserve that ideal. Okay? And it's a feature that if you look at these guys there, you can even figure out what local generators for this sheaf look like. And they look like this. So Z here is like if you pick one non-vanishing section and pair with S gives you a function, I'm calling it Z. And then I just have like Z, Z bar, and a bunch of other coordinates like extended to coordinate system on a manifold. And then you see that these guys here together generate the sheaf. So this is a locally free generated sheaf, so it comes from a vector bundle, okay? So this is from that point of view, it comes from a vector bundle, and these guys are the basis, local basis for my vector bundle. So like this one here, that's something that some people have some difficulty grasping first time around. From this point of view, I do have a vector bundle, and each one of these guys, including the first one, is a non-zero section, okay? It's just that somehow this vector bundle that I'm describing for you here comes out right away with a map to the tangent bundle, and if I map this guy here to the tangent bundle, over z equals to 0, it kills. It's in the kernel. So this sheaf here is locally free, so I do get a vector bundle. I'm going to call this vector bundle T minus log D. And the Lie bracket on section, on vector fields actually gives rise to a Lie bracket on these guys here, which makes it into a Lie algebroid as well. And this is to say just that it's a Lie algebroid. So the inclusion is a bracket preserving map. So it's a complex Lie algebroid. And you can compute its cohomology. That's one good thing. Lie algebras come with cohomology, and you can go and compute. This one in particular is something that people from complex geometry had already encountered, so they kind of had computed the cohomology already, but it was always on a complex manifold. And I guess the point of view is that there's no complex geometry behind it, even though that's how it was done before. Whatever techniques they had, you can just go and repeat them, and you get the cohomology of this Lie algebroid, just the cohomology of the complement of the divisor. Okay? Then, okay, I'm talking about the cohomology. I might quite well look at the dual space. So T minus log D star, which then I just drop the minus, because that's somehow the dual thing. And what is locally generated by, so these are the corresponding dual forms. So d log z is the dual of z d dz.
So this is the Lie algebraic cohomology of that T log T.
Yeah.
Is the cohomology of the...
It's isomorphic to the cohomology of the complement. So somehow it's not a, like if you look at the differential operator, it's not elliptic, of course, but the cohomology is still finite dimensional and still gets to compute this. And you can actually go and describe what the forms look like. So now the difference between usual theorem forms that now you have this d log z, which is a bona fide element in your dual space. So you can actually use that in your forms. And now you look back at your generalized complex structure, the one that's the stable one. I'll just write what the stable one looked like here. A stable generalized complex structure. I mentioned that because of Bailey's result, it was always the exponential of d log z, wedge, I don't remember what I used before, some form here, alpha plus omega 0. So when you look at this kind of form, you see right away that this is just the exponential of a 2 form on this Lie algebroid. So the idea is that I made my tangent space a little bit more complicated. I'm not dealing directly with the tangent space, but a different Lie algebroid. And what I gained out of that is that my generalized complex structure became simpler. It just became a smooth 2 form, okay? And what else? There's this thing here. So like the non-degeneracy condition is just that the imaginary part of this 2 form is symplectic. But why do I say symplectic? There's a little issue here, which is why I cannot just stop at this slide, because T minus log D is a complex Lie algebroid. If you look at here, these guys here, see that complex conjugation does not preserve this generator. So like D log Z bar is not there. So taking imaginary part is an operation I'm not allowed to do within the Lie algebroid cohomology. So kind of formally, I understand perfectly what imaginary part of omega is, but it certainly is not a 2 form on the Lie algebroid. So it remains the question of where it belongs. So it's certainly not here, the imaginary part of omega, because it would involve a d log z bar, which is not allowed. Okay, so we go on. So the next thing is say, well, if we have a line bundle with transverse section as we had before, I can take U tensor U bar and S tensor S bar, and now I get a real line bundle with section as well, but it's not transverse anymore. So what is this? This is going to be what we call an elliptic divisor. So it's this real line bundle with a section which vanishes along the manifold I'm interested in. So a codimension 2 manifold, real codimension 2, and for which the normal Hessian is positive definite. So in particular, it's a Morse-Bott function. Okay? So that's what would you get if you do something like S tensor S bar, because then if you look in local trivialization, it's like S times Z times Z bar. So you're getting like the norm of Z squared. So it's a positive definite Morse-Bott function in there. So this is kind of where it should belong, because this is giving me now a real line bundle. Like everything became real now. So if I can construct a Lie algebroid out of this, it's going to be a real one, and taking imaginary part should be allowed. So I can try to repeat the same story. This thing here will determine me an ideal on C infinity functions. Namely, I just pair dual sections with this section here. And I can look at the vector fields which preserve that ideal, and I get something like this. Z dz and Z bar dz bar, because these are the guys which preserve like distance square, Z times Z bar. And I get the remaining coordinates that just keep on going like that, -4. Okay, so I do get to describe what the sheaf of vector fields preserving the ideal is. And again, I look at it and say, I'm lucky. I still have the correct number of sections. It's still a locally free sheaf. So I still get a Lie algebroid out of this. So it's an involutive, locally free sheaf. And again, I have a Lie algebroid over M. But now I have both Z dz and Z bar dz bar appearing there. Okay, and kind of part of just worth mentioning, like part of the reason to do all this is that the most natural thing one would look like, which we are not doing, is say, well, we have D, and you could look, so it's like what doesn't work, which would be the first thing one does not work. One would look like, look for, is to pick up, for example, the set of all vector fields in M, such that X on D is tangent to D. That would be the tangent sheaf. So that works fine for codimension 1 things, but for codimension 2, it's not locally free anymore. So the most natural thing that you could do does not give you a Lie algebroid, but somehow once you start putting this real or the complex line bundle with some extra conditions, you cook up Lie algebroids out of that. So like what is this guy in local coordinates, in polar coordinates? So I would like to make everything real instead of z's and the z bars. Then you get the r ddr and the dd theta, so the angular coordinates around d and the remaining guys. We have natural maps, so like if you restrict it to d, this is like a C star bundle, or R2 bundle over D. So it really looks like I have a corresponding projection to D. So this guy restricted to D is actually a Lie algebroid over D. That looks like this C star bundle over D. If we have the DD bar, the DDR, and the D theta. So as far as the Lie algebroid goes, you look at the generators of this Lie algebroid, it looks a lot like the C star invariant vector fields on the normal bundle over D. So that gives you a way to compare sections of your Lie algebroid with sections of this C star bundle over D, and you have also the corresponding map for the complement, where it's an isomorphism. And these two things together give you an isomorphism cohomology. You can again compute the cohomology of this guy. This was not done in complex geometry before, but essentially it's the same sort of techniques. And it is the cohomology of the complement plus some extra term here, which is the cohomology of the S1 bundle of the normal bundle of D. So now it's not, you see a little bit more than just the complement of your manifold. Okay. You get residue maps, so it's just good to keep that in mind. So like what are the relations? So I have a bunch of Lie algebroids, I have the forms on the manifold, and these things are related. So for example, on this elliptic tangent space, I have a residue map which is just to take the coefficient of d log r d theta. Okay, so that's a map of complexes. And then when I look at it, because it's a map of complex, I can look at the kernel, and that's again a complex. So the kernel is a subcomplex called the zero residue forms. I call this map the residue map. And that's an interesting one, because essentially the residue, just keep in mind where I want to go, the residue is the coefficient of d log r wedge d theta, or if you like, d log z wedge d log z bar. But my structures, they look like this. There is no d log z bar here. So this guy here is a 2 form which has no d log z bar in it and therefore has no residue. So somehow I could look at these general forms on this elliptic Lie algebroid, but I'm clearly not interested in all of them because the ones that arise from giant complex geometry have automatically 0 residue. So I'm forced to look into this subcomplex here. And it's interesting to compare now. So like there's a comparison map. Because before I had a 2 form here, and I want to take its imaginary part. And the problem I had is that taking the imaginary part landed me out of my space. Where did it land? It landed here. In fact, it lands in the 0 residue forms, okay? And if you look at what the kernel of this map is, it's precisely a smooth form. So this is something that works in general. Of course, I'm more concerned in the case when k is equal to 2, because I know my giant complex structure is a 2 form here, a stable giant complex structure is a 2 form here. And if I take the imaginary part of it, I get a 0 residue 2 form. And what am I losing when I do that? I'm just losing the B field. So I'm just losing gauge symmetry. So a giant complex structure is actually equivalent to just a symplectic, 0 residue symplectic 2 form here. Stable giant complex structure, if divisor D, is equivalent to 0 residue symplectic structure on this space. Okay? So now there is no taking some imaginary part and landing somewhere else. So I can really translate it. Stable is the same thing as symplectic somewhere. And hopefully that is of some use. Okay? But that's the point. So I try to simplify my structure by looking at maybe a more complicated space to encase it. But once you do that, you have symplectic techniques available to you. Okay? You have Moser trick and that kind of thing. So you can use symplectic techniques to describe this type of structures. So the first theorem we have is just say, okay, so these structures, they clearly are singular along this D. Outside of D, they are symplectic type, so that we understand well enough. And what happens on D? What do they look like? So we have to do 2 things. We have to find out a bunch of invariants that the structure determine on that D. And you should also check if these invariants are all. Ideally, that would be, like you tell me all the invariants and they determine a neighborhood. And because we are close enough to symplectic geometry, that still works. So there are two things here. One of them just to say which invariance does it determine. So a stable generalized complex structure determines the following data on its singular locus. First, D becomes a type 1 generalized Calabi-Yau. So remember, generalized Calabi-Yau is the one defined by a closed form, and the type has to do with the degree of the leading term, the composable form. So it's a type 1 generalized Calabi-Yau. And after that, there is also a generalized holomorphic structure in the normal bundle for which the pairing of the co-Higgs field with the degree 1 part is constant. Okay, non-zero. Okay, so there is like a generalized holomorphic structure in the normal bundle. I think that's enough to remember that. And this is all the structure there is. So if you give me two that induce the same structure, they have equivalent neighborhoods. So this is a full neighborhood theorem, so it's answering the question. What do they look like? And now not just on points, but on the neighborhood of this interesting submanifold. So the proof, I'm not going to give the proof, actually, but I would just like to say like what comes up in the proof. One thing is that you have to check that the stated data encodes what's the first order information of the generalized Calabi-Yau structure, and should be able to get of the generalized complex structure. Should get the generalized Calabi-Yau, you should be able to get this holomorphic structure, and then hopefully you can go back as well. So the step to go and find the data has nothing to do with what I have been telling you, it's just something you can just do by hand. So if you pick your generalized complex structure, you write it as e to the b plus I omega, where this b plus I omega is here, and then just take the residue. So this is the complex residue, and the complex residue is the generalized Calabi-Yau structure. So that's how it arises. It's just the residue of the generalized complex structure. So the generalized Calabi-Yau structure is simple to determine. And the other one is also simple because you look at this anti-canonical section. Since it's transverse, it gives you an isomorphism between the normal bundle and the anti-canonical bundle. And this thing here is generalized holomorphic. So you can use this isomorphism to pull back the generalized holomorphic structure. So getting the type 1 generalized Calabi-Yau and the holomorphic structure is somewhat easy. And the question is, how do you go back then? And that's the bit that I really want to do. But essentially, you translate all this data here into symplectic data, into this zero residue symplectic form. And you check that what it means, it really is that you have the hypothesis of the Moser lemma. So if two guys give you the same data, then the underlying symplectic structure agrees on D, and they determine the same cohomology class. So you can use this Moser type of trick to flow from one to the other, and you get the isomorphisms that you need. So that's really like, that's the advantage. So that's the point. You translated your generalized complex structures, your generalized complex problem into symplectic one, and you can use symplectic techniques, and that's like the first, most obvious thing to do. Use Moser trick to get the diffeomorphism. So let's see here what the example is now. Okay, yes. So this is another example of a similar thing. So if you just give me any manifold, so right now L has no structure whatsoever, but L stands for Lagrangian, so you know where we're going. You look at L and pick any submanifold of codimension 2, which is actually an elliptic divisor. Then you can look at the total space of this bundle here, T star log D. And just as in the symplectic case, you get a canonical form, canonical 1 form, like a tautological 1 form. Here you also have a tautological 1 form on this space. And if you take D of this tautological 1 form, you get a zero residue symplectic structure on the total space of this thing, for which the divisor is the inverse image of D. Okay? So, and the zero section is Lagrangian. It's a brain for this structure. And you can actually check that this is all you can get, in the same way that all Lagrangians have a standard neighborhood theorem for the symplectic case. If you have Lagrangians which intersect transversely your type change locus, you also get a corresponding neighborhood theorem here. So if you have a stable generalized complex manifold with singular locus D, and L is a Lagrangian brain, which is to say that it's Lagrangian in the symplectic locus, and a Lagrangian brain which intersects D transversally, then generalized complex structure in a neighborhood of L is isomorphic to the one you get in this example here, which is essentially T star of L. So this kind of thing that you get also from symplectic, again, it's a case of Moser argument. Okay, so it's another trick. You say, transport everything into the symplectic world, and see what you're getting here. And again, it's the case of having two symplectic forms which agree on the submanifold and allow you to do the flow that you'd like to do. So another thing that one can do in symplectic geometry that has had some success, a lot of success in a way, is to look for maps symplectic manifolds admit. So that started with work of Donaldson first he wanted to find symplectic submanifolds and check that every symplectic manifold has a symplectic submanifold of codimension 2. And later he improved that to say that every symplectic manifold admits a Lefschetz pencil. And later Gompf proved converses to this theorem, saying that every manifold which admits some sort of pencil has a symplectic structure, has to add a whole bunch of hypotheses. But there is some sort of two-way street there, that every symplectic manifold has a Lefschetz pencil, and every Lefschetz pencil has a symplectic structure. So here I would like to kind of go one way or the other. So that's the idea here. And what you could do is kind of pick two manifolds with elliptic divisors and try to repeat that kind of argument. And it doesn't take much to actually repeat the argument, so I'm not going to do it here. So that would be maps between manifolds with elliptic divisors. You could just try to pull back a Jones complex structure here and wedge with a fiber-wise symplectic structure. So that's really what Gompf does, and you have to adjust very little to repeat that kind of thing here. Maybe it's not so interesting to do that, because it really is like repeat what Gompf does for symplectic structures. Now, one thing you can do, which is a little bit more interesting, is not put the base itself don't put the structure of a symplectic elliptic divisor on the base. In the base, I'll put the structure of a real divisor. Okay, real divisor is something that appeared yesterday, and my real divisor is not your real divisor. So my real divisor is just really the zero of a transverse section of a real line bundle. Okay, so like I have complex divisor because I have transverse sections of complex line bundles, but if I have transverse sections of a real line bundle, I could talk about real divisor. And in many senses, you can think of this as really a manifold with boundary. So this should be like a surface which has a bunch of circles in the boundary, okay? So you can look at maps that map your manifold with elliptic divisor into manifolds with boundary. And you can require a few properties. For example, that D is the preimage of the boundary. And the normal Hessian is actually positive definite over the boundary. And outside this D and Z, where I have specified singular behavior because of this thing here, I should have only nice singularities, so Lefschetz type singularities. And besides those, so the rest of it, the map should be a fibration, and the fiber should be homologically essential, so it should be homologically non-zero. If you have that, then you actually can put a stable Jones complex structure on M, for which D is the type change locus. So this is saying that if I have some sort of Lefschetz vibration normally would be conditions 3 and 4. And now I'm adding a new singular locus and putting a new normal form to deal with that singular locus. So this is kind of a generalization of a Lefschetz vibration from symplectic geometry. And I'm saying that if you have this generalization of symplectic vibration over a manifold with boundary, then you should be able to produce generalized complex manifolds. So that's the Gompf's theorem for symplectic manifolds would look like this. Okay, the proof, I started at 2. Okay, so let me just try to very quickly go through the proof. So the idea is that the fact that the way it's phrased means that if you pull back the ideal defining the boundary of your sigma, gives you the ideal for the elliptic divisor, and that means you can pull back log forms on the base. So if you have a form that has a log singularity, like a log singularity along the boundary, you can pull that back, and that gives you a log form also on the original space, on the domain of your map. So that means that you can actually get this map of Lie algebroids, in particular, can pull back cohomology classes. And what you do is that you put a B Poisson structure on the base. So that's kind of the log version of a symplectic structure on the base. And you pull it back to get a 2 form that's well defined as a log form on the whole space. And you want to edge that with a fiber-wise symplectic structure on M. So that's like the standard way to construct symplectic forms. If you think it's like one of the first ways to construct interesting examples of symplectic manifolds was like that. You pull back a symplectic structure from the fiber and wedge that with a fiber-wise symplectic structure on the total space. And the idea is that with the hypothesis we have, this can be done also over D. And there's a little trick thing going on there, because over D, of course, the fibers, they drop dimension. But even then, you still get a symplectic form going on there. So there is to get this, you actually need to do some local forms and whatnot. But eventually, you kind of can, once you have dealt with the technicality of the present situation, you really fall back into Thurston Gompf type of arguments to get the symplectic structure on the total space. In particular, the nodal singularities that are there is something that have already been dealt with. so you don't have to worry about those. And you just get just after you have dealt with the singularity on D, the rest of it is kind of easy to do. So some remarks about this. So once you get one of these Lefschetz-like vibrations, then what do I have? So because of the behavior of this map in the neighborhood of D, I have very restricted fibers. Like I cannot have whatever fibers. The fibers are automatically tori, 2D tori. And that's why I'm talking about it here, because 2D tori are good for duality. I'm not going to tell you what the dual of this thing is. But essentially, that's like these are ideal spaces for you to look into and say, what can I do here? What kind of T-duality can be done to these spaces? What can you propose as mirrors for this thing? So right away, you get that whenever I have one of these vibrations, I'm describing for you a 4-manifold, which is a torus vibration. And besides that, the monodromy of a loop near a component of the boundary is automatically a power of the twist as well. And I just give a name here. So I'm calling these maps that we have just introduced Lie algebroid Lefschetz vibration. So whenever you encounter one of these, you have a stable generalized complex structure. And they are automatically torus vibrations. And there is some restriction on the monodromy along the boundary of your manifold. So here's an example, just so we can, like, is this, maybe it's too abstract, but it is that you can actually compute things. You can actually construct manifolds this way, okay? So this is a Lefschetz vibration for you over the disk with boundary. And the idea to describe a Lefschetz vibration should pick a regular fiber for reference. And here I've marked my singular fibers. In this case, I have 3 singular fibers. And what you have to do is pick a path connecting your reference fiber, reference regular fiber to the singular ones, and tell me which cycle is collapsing. So like these singular fibers are pinched tori. And if I pick a specific path, I can actually tell you which cycle is collapsing in this pinched torus. So the idea here is that you get these 3 things here. And for this particular combination in which I have A plus 3B, A minus 3B, and A, where A and B are generators of the homology of the torus, then the monodromy around the boundary is 9 times B. So it's precisely one of these things that I can use to produce stable structures. So the monodromy is 9 times B. So the result is that whatever this picture here is giving you is a stable generalized complex manifold. Fact. Now, of course, it would be nice if I could tell you which manifold it is, and that is that's a matter of like playing around. So you have to have some skills for that. I don't know, but it's Kirby calculus. It's like in a way, it's not particularly difficult because Lefschetz vibrations have very easy Kirby diagrams. So I just have to figure out where to put the last handle. But anyway, you can actually go and figure it out. And in this case, this manifold with this divisor is just CP2 with a cubic. Okay? But that's a computation you have to do. I'm not telling you how to do that. But essentially, I'm giving you a vibration, which by the looks of it, you right away know it is a stable generalized complex manifold. And the question is just, which manifold is this? Does it have a name? In this case, it did have a name. You can repeat the same thing now with more fibers. So this is kind of the same thing, but with many fibers. I don't know how many. 2n minus 1 plus 1. Yeah. Anyway, so I have here one with many fibers, and I'm choosing these numbers here so that when you do the composition of the monodromies, you do get that the monodromy around the boundary is a power of the twist. In fact, it's 10n minus 1 times b again. Okay, so that means that I can actually extend this to something over the boundary and get one of these Lie algebroid Lefschetz vibration, and I get the generalized complex structure on this space as well. Which space is this? So again, satisfies the property of the theorem, so I get a stable generalized complex structure. And in this case, again, have to do your Kirby calculus to get that this is the manifold you obtain. Connected sums of 2n plus 1 CP2s, okay? So these are kind of interesting spaces because they are not symplectic, they are not complex, they are not holomorphic Poisson. So they are not of the 3 initial classes I talked about, okay? So I'm saying that we do have these stable structures in spaces which do not have just complex or symplectic structure, yes?
What's the structure of the divisor here?
It's again a torus. It's an elliptic, like it's automatically a complex submanifold.
So it's an elliptic curve.
It's an elliptic curve, yes. We can even establish what the intersection is with the different CP2s you have here. It kind of has a pattern. It's intersects 3 times one generator, 1 times another, 3, 1, 3, 1, 3, 1. So this is like the general principle here. is that if you give me a map from M to C, which is a proper genus 1 Lefschetz vibration with homological essential fibers, if the monodromy around infinity is a power of the twist, then we can first compactify M by adding this elliptic divisor at infinity, compactify C to D2, so that the map now extends to a map from M bar to D2. And this whole thing here that I'm producing is a Lie algebroid Lefschetz vibration. So these are the examples I just produced. Like, if you want to formalize it, that's what you have. And this guy here will always admit a stable giant complex structure, and the singular locus is precisely the thing that you added at infinity. So there's a torus where there is the type change. If you're doing symplectic geometry, you might ignore this. Like, if you're interested in symplectic geometry, you might say, well, no, I'm completely fine with this, you know. Here I have my symplectic manifold. Here I have C, which is also fine, and I have a Lefschetz vibration, proper map, like, what? Why would I do anything about this? And that's the interesting thing, that these kind of things have appeared before. So people have studied these things. They appear in the context of mirror symmetry. Denis, Katsarkov, and Orlov, I think. Orlov. They actually had, sorry, let me just go back a second. They had this picture, actually. So they proposed that the mirror to some funnel should be this open symplectic manifold, and the projection map is a superpotential, and they are fine saying that this is like just an open, big, complete symplectic manifold. So from a certain point of view, these things have been around, and they have appeared in the context of mirror symmetry. And kind of what I'm hoping, at least, is that what they were seeing is the stable giant complex structure, except that if you're doing symplectic geometry, you may not feel the need to compactify it. But the idea is that it actually is a compact manifold behind it, and probably the mirror of the funnel should have been this stable one here, not some Landau-Ginzburg model. Okay? So that's the idea. I have 5 minutes. Just to mention, this is a one-way street, because in the symplectic case, there is this, it's nice that you have, Donaldson tells you, symplectic manifolds give you Lefschetz pencils. And Gompf tells you that Lefschetz pencils give you symplectic manifolds. So the hypotheses don't quite match, but it gives you a general feeling that's a two-way street. You can go from one to the other and back. In our case, we do know that it's not true, because we don't have pencils. That's a kind of, if you first point down, why is it not true? Because we don't have pencils. We have Lefschetz vibrations. And it's not even true in the symplectic world that every symplectic manifold admits a Lefschetz vibration. They admit a Lefschetz pencil. So here also true for stable ones. Of course, even like the first remark that if you just pick CP2 with a standard symplectic structure, it does not admit a Lefschetz vibration over any surface. Done. So it's already not true in the symplectic case. You do need the notion of pencil, which we are lacking at the moment. But in our case, you can actually argue that if you had one of these stable ones, then on the one hand, we do know that any finitely presented group arises as a fundamental group of a stable structure. That's something that following Gompf's type of arguments you can prove for a stable structure as well. Rafael Torres did that in 2011. But for these Lie algebroid Lefschetz vibrations, we always have a short exact sequence. So the pi1 of the total space is kind of restricted. You have here the free group on n generators, and you have Z2, and should sit inside such a small sequence. So that in itself tells you will not get all the possible finitely presented groups this way. So we do know, for topological reasons, that not every stable giant complex structure appears as one of these Lefschetz vibrations. I probably should stop. Yeah, I won't continue. So essentially, you can apply more symplectic techniques to these guys. They have good behavior because we have this normal form theorem. Symplexically, they are like very nice type of symplectic manifold. So if you remove the singular locus, you get this open symplectic manifold, which is kind of concave and convex at infinity. So Gromov-Witten theory can be developed for these manifolds. And hopefully can also do Cyber-Witten theory. And kind of one of the questions is just how to put the divisor at infinity and still say something meaningful. But just from the fact that you can do Gromov-Witten theory and Cyber-Witten theory to these things, puts some constraints on the manifold. So I'll just stop here, but just say that more advanced differential techniques can be used in the spaces because they are so close to being symplectic. So this is kind of a rich type of giant complex structures that is so rich because it is close to symplectic geometry. Thank you.